Binary framing in Hypertext Transfer Protocol version 2 allows remote procedure calls to saturate high-speed network links, while JavaScript object notation parsing consumes excessive processor cycles during peak loads. Protocol buffers eliminate the overhead of field names by using numbered tags, which reduces the payload size by over 60% compared to text-based data formats like JavaScript object notation. The transport layer uses a single transmission control protocol connection to send multiple parallel streams of binary data simultaneously, effectively removing the head-of-line blocking issues found in older protocols. Converting text strings into memory objects requires intensive string scanning and memory allocation, creating a massive bottleneck in high-throughput representational state transfer APIs when processing thousands of requests per second. Binary protocols utilize pre-allocated buffers and fixed-size fields to minimize the frequency of garbage collection cycles, which directly improves the stability of tail latency in high-volume production systems. Hypertext Transfer Protocol version 2 implements header compression by maintaining a dynamic table of previously sent metadata, which significantly reduces the data volume for every request sent across the wire. Reusing an established connection avoids the repeated latency of the transmission control protocol handshake and the transport layer security negotiation, allowing for much higher throughput over long-lived communication channels. Our benchmarking environment uses a cluster of 3 microservices on Kubernetes to measure maximum requests per second, while monitoring the point where latency hits the 99th percentile limit.
We use dedicated load testing tools to generate millions of binary requests per second, ensuring the client hardware is not the bottleneck during the throughput measurement of the target service. Throughput is meaningless without context on tail latency, as system analysts must ensure that 99% of requests are handled within acceptable timeframes under maximum sustained load conditions. Handling 10,000 parallel requests requires efficient thread management, where the binary protocol often outperforms text-based services due to lower per-request memory overhead and faster marshalling speeds. The asynchronous nature of the binary framework reduces context switching between worker threads, allowing the processor to spend more time on application logic rather than managing internal system overhead. Non-blocking input-output operations allow the server to handle multiple requests on a single thread, which is essential for maximizing throughput in high-density microservice architectures. Marshalling structured data into a binary stream takes less than half the time of serializing the same data into a string, which directly scales the maximum achievable throughput of the service. Using technologies like flat buffers allows for zero-copy deserialization, where the application accesses data directly from the buffer without a dedicated parsing step, pushing throughput to the hardware limit. Zero-copy mechanisms move data directly from the network interface card to user space memory, bypassing the operating system kernel and saving precious clock cycles for the application.
Transitioning to Hypertext Transfer Protocol version 3 further improves throughput by using the Quick User Datagram Protocol Internet Connection Protocol to eliminate head-of-line blocking at the packet level. While compressing JavaScript object notation with gzip can reduce data size, it adds significant central processing unit overhead compared to the natively compact binary encoding of protocol buffers. Unmarshalling binary data is a linear operation based on byte position, whereas text parsing involves complex state machines to identify delimiters, quotes, and escapes characters within the payload. Binary protocols enforce schemas at the compilation stage, which removes the need for expensive runtime validation checks that typically slow down traditional representational state transfer request processing pipelines operations. Generated code for binary protocols uses native data types, which allows the compiler to optimize the machine code for maximum speed, unlike dynamic type checking in many web frameworks. Implementing client-side load balancing allows the system to distribute traffic across backends without a centralized proxy, removing a potential throughput bottleneck and reducing network hop latency. In a service mesh, every request passes through a sidecar proxy like Envoy, which adds a few microseconds of latency but optimizes binary frame routing for high-scale throughput.
Encryption is the primary bottleneck for throughput in secure environments, so using modern cryptographic libraries and hardware acceleration is mandatory to maintain high performance in binary communication.
Streaming responses allow the server to send data chunks as they become available, which maximizes throughput for large datasets by avoiding the need to buffer the entire response in memory. Bidirectional streaming enables simultaneous communication, where both client and server can push data through the pipe, drastically increasing throughput for interactive or real-time synchronization tasks. The binary protocol implements flow control to prevent a fast sender from overwhelming a slow receiver, ensuring that the system throughput remains stable without dropping packets under heavy congestion. Throughput can be limited by the transmission control protocol window size, so analysts must tune kernel parameters to allow enough unacknowledged data to be in flight across high bandwidth connections. Standard web browsers do not fully support the binary protocol features natively, requiring a translation layer that can reduce throughput compared to direct server-to-server binary communication. Using a bridge to connect web clients to binary services introduces extra marshalling steps, which can negate some of the performance benefits of using a binary protocol in the first place. Load balancers must be capable of understanding the binary protocol frames to distribute requests correctly across a cluster, as traditional round-robin at the connection level can lead to unbalanced loads. Long-lived connections can cause hotspots where one server receives most of the traffic, requiring rebalancing strategies like max connection ages to ensure throughput is distributed evenly across all nodes.
Increasing throughput is often achieved by adding more replicas of a service, provided the load balancer and the network fabric can handle the increased volume of binary traffic. When throughput plateaus despite low network usage, it often indicates that the processor is saturated by serialization tasks or business logic, requiring a more efficient data format or better algorithms. System analysts must monitor container resource limits, as hitting memory or processor caps will trigger throttling that drastically reduces the throughput and increases the latency of the service. Higher throughput and lower resource usage directly translate to lower cloud infrastructure costs, making the choice of an efficient binary protocol a financial decision as much as a technical one. Adding a complex API gateway for authentication and rate limiting can reduce total system throughput by up to 30% if the gateway is not optimized for binary protocol transparent proxying. While protocol buffers are standard, other formats like Avro or MessagePack offer different trade-offs in terms of schema evolution and serialization speed that can impact overall system throughput. Representing floating point numbers in text requires many bytes and complex parsing, while binary formats store them in fixed 4 or 8-byte fields for instant access and zero precision loss. In a multiplexed connection, a single lost packet can stall all concurrent streams, making it essential to monitor network health when aiming for maximum throughput in high-performance environments.
Implementing exponential backoff for retries during periods of high congestion prevents the thundering herd problem, which can otherwise crash a service and reduce total throughput to zero. Representational state transfer maintains a throughput advantage in read-heavy scenarios, where content can be cached at the network edge by standard proxies and content delivery networks combined. In our tests, binary protocols achieved 4 times higher throughput than text-based APIs on the same hardware, primarily due to reduced payload size and lower processor utilization during serialization. For internal microservices requiring massive data exchange, binary protocols are the clear winner, while representational state transfer remains appropriate for public-facing web APIs with standard caching needs. System analysts must choose the protocol based on the specific bottleneck, whether it is network bandwidth, processor capacity, or the requirement for browser compatibility in the final application. Designing for high throughput from the start involves selecting binary formats and optimized transport layers that can grow with your system load, without requiring a complete rewrite of the communication layer. Continuous monitoring of throughput and latency in production allows for iterative tuning of buffer sizes and connection limits to ensure the system remains at peak performance as traffic patterns evolve. The choice between binary and text protocols determines the ultimate throughput ceiling of your architecture, making it one of the most significant decisions a system analyst will face in modern IT development.